Hello everyone, this is Fluid Mechanics for the 30th of October 2014, class number 20. As you already know, this lecture is posted online. We won't be meeting in person this Thursday. I'm down in Clemson working on the FE exam, so you'll be watching class on your own. A couple of announcements to go over. First of all, the Jet Impact Lab that we did on Tuesday, that will be due on November 4th, next Tuesday, in lab. Homework 5A is due today, even though we're not meeting in person for class. And as I explained on Tuesday, what you need to do is submit that assignment to my box, the metal box beside my office door, by 11 a.m. on Thursday the 30th. There's a folder there that has the number 318 on it, and you need to just slip your assignment into there, and the grader will pick it up at 11. 11 a.m. is the strict deadline. Homework 5B, you can see there. It's also listed in the course schedule that I provided at the beginning of the semester. That will be due on Thursday, the 6th of November. Today we continue our discussion of concepts from Chapter 5. We're going to go over the Reynolds transport theorem and how that it's applied to reservoirs. Just as a note, the majority of this recording was prepared a different semester, so there may be a handful of references during the recording where it says last Wednesday in class or something like that, and so obviously those references don't apply, but all of the content material is the same.
We'll start off with another application of the continuity example. In a lot of cases, continuity is used to keep track of liquid level elevations, and one instance in which this is important is when taking a look at the amount of water that's in a reservoir at any given time. In this example, we know that water comes into a reservoir at a flow rate of 11,330 cubic meters per second, and it's discharged through a dam at 7,080 cubic meters per second. At this instant in time that we're looking at, the surface area of the reservoir is 10,360 hectares, and we want to find out how quickly the water is rising at that particular time. We want to first find the Q rise. Q is, of course, a volumetric variable, so we'll find the difference between the in and the out in terms of the volume, cubic meters per second, that's accumulating inside the reservoir, and then we'll use that along with the area of the reservoir in order to find the velocity that the water is rising. In this example, we're working with a reservoir that has a volume of 11,300, it's the flow rate into a reservoir. We've got a reservoir depicted, and there's a dam on the edge. Here's the water, and the flow in, Q, is 11,330 cubic meters per second. The flow out of the reservoir through a penstock, Q out, is 7,080 cubic meters per second. At this particular time, the area is 10,360 hectares. We want to find out what is the rate of rise. Alright, what we could say as a general rule is that in the continuity equation there's going to be accumulation is in minus out, and in this case we have a flow rate in of 11,330 cubic meters per second. The flow rate out is 7,080 cubic meters per second, and so the difference between the two is 4,250 cubic meters per second. That is the Q rise. That is the flow rate, the net flow rate that's causing the liquid level to rise in the reservoir. Now, taking into account the area, for an area of 10,360 hectares, the unit of a hectare is probably unfamiliar to many of you. There are 10,000 square meters in a hectare. So that works out to, for this reservoir, it has a surface area of 1.036 times 10 to the 8th square meters. If we want to find out the velocity that the water level is rising, we can do that with the following formula, which is based on Q equals VA. And you've had to use that a couple of times, including in the recent lab. If we rearrange that, that is that the velocity that the liquid level is going to rise will be the Q rise, which was the net accumulation of liquid in the reservoir, divided by the area of the reservoir. And so applying that, there was a Q rise of 4,250 cubic meters per second, and the cross-sectional area of the reservoir is 1.036 times 10 to the 8th meters squared, which means that the liquid level V rise is going up very, very slowly, 4.102 times 10 to the minus 5th meters per second. If we want to find that on an hourly basis, then the value simply needs to be multiplied by the number of seconds per hour. And that is 0.148 meters per hour. In other words, it's going up at 14.8 centimeters per hour as a result of the difference between the flow rate in, which is large, and the relatively smaller flow rate out. And that's how we can calculate the rate of rise in the case of a reservoir. Another instance in which continuity equation is applied is where you're looking at the liquid level and how it decreases as water flows through an orifice, which is an opening in a tank that water exits through. The velocity that water shoots out of an orifice is a function of the height of the water surface above the orifice opening. And one of the things that we remember from the Reynolds transport theorem is that this imaginary control volume that we're using to keep track of where our control surfaces are and what's inside of the boundaries, we monitor the accumulation of mass over time. The shape of the control volume can change over time, meaning that as the liquid level decreases, we can adjust the control surface heights that we're constantly just barely enclosing the liquid level that's inside of a tank. Now, the derivation of the orifice equation comes from the application of Bernoulli's equation. And in Bernoulli's equation, what we do to come up with the orifice equation is we set the pressure head and the velocity head at 1 equal to 0, meaning that we're comparing conditions at the top of a reservoir to the conditions as at the exit of an orifice, the jet that's coming out of the orifice. And so the only thing that there will be at 1, which is where the water surface is at the top of a reservoir, is the elevation term Z1. And then at location 2, where it's a jet of water coming out of a tank, we cancel out the pressure head term and the elevation head term, and we're left only with the velocity head term. And so this square root of 2gh is just rearranging Bernoulli's equation, where we've set the pressure head at 1 and the velocity head at 1 equal to 0, and then at 2 setting the pressure head equal to 0, so that what's left is the elevation term, so that delta z, the change in elevation between 2 points, is h. And that's how we can find the velocity as water comes out of a jet. And you can see here that h is the measurement from the center line of the orifice, so it's the center of the opening, up to the water surface. And we'll often apply the orifice equation in conjunction with the continuity equation. And the continuity equation, as represented here, says that the mass inside the control volume is the difference between the mass, the change in mass over time. So dm dt means the mass inside of the control volume as it changes over time is due to the mass flow rate in through control surfaces and the mass flow rate out through control surfaces. The control surfaces are those boundaries within the control volume that liquids either enter or exit the control volume. And here, as depicted, there's no flow in, there's only flow out. And so we can find an equation that will relate how long it takes for a tank to empty if we consider the change in water elevation over time. So here in the equation, what that's saying is that V1A1, so that's the flow rate out from the tank, is equal to the rate of loss inside of the control volume. So this is the flow rate out, mass flow rate, volumetric flow rate at this point, since we're just working in terms of volume, velocity and area. We haven't yet multiplied anything by density. And this is the change in volume over time inside of the tank. And so A sub T is the cross-sectional area of the tank, and dHdt is the change in the water height over time. So the elevation is decreasing over time, and if we substitute in the orifice equation for the velocity here at the outlet, where the orifice equation is the square root of 2gh, and solve for dt, we can integrate that to find the amount of time it takes for the liquid level to fall some distance h. And if you say at t0 you're going to let the height of the water equal some initial height, then the time it takes to fall from the initial height to some other height h can be calculated as shown. So you can solve for the amount of time it takes. Now, as you'd expect, how quickly a tank empties or fills is going to be dependent on the size of the orifice opening and also the cross-sectional area of whatever this tank is. A swimming pool is an example of a tank that the water level changes very slowly because it's got such a large surface area. The A sub T for a swimming pool is big because swimming pools have a large surface area, and if you're draining a swimming pool with a garden hose, it's going to take a very large T for the liquid level to drop. On the other hand, if you have a very large cross-sectional area here, if the area of the opening, the orifice, is large, then that's going to decrease the amount of time it takes to fall some liquid level. So we'll apply that with this example, and we're looking at unsteady flow here. Remember, the definition of unsteady flow is that conditions are changing with respect to time. And what's changing over time is that as the water level decreases, so does the velocity rate out of the orifice. We have a circular tank. The diameter of the top of the tank is given as 500 millimeters. In other words, it's a half meter in diameter. The opening of this orifice that water is shooting out of is 15 centimeters, 0.15 meters. The initial height of the water surface is 2.5 meters above the center of the orifice opening, and we want to find out how long will it take to fall 1.1 meters. And then the second part of this example that we're going to solve is how long does it take to fall an additional 1.1 meters. Alright, in this example we're going to be looking at a tank that has an opening in the side, an orifice. There's water inside the tank, and water is coming out of the orifice as a jet. To begin, I'll derive the orifice equation from Bernoulli's equation. Remember that Bernoulli's equation is the pressure head, the elevation head, and the velocity head at 1 equal to the pressure head, the elevation head, and the velocity head at 2. And what we're going to be using as 1 is the top of the water, and 2 will be as the water has come out of that tank and is now issuing as a jet. At 1, since it's in contact with the air and this tank is open to the atmosphere, then that means we can cancel out the pressure head term. Also, the water at the top of the tank isn't moving. We assume that maybe the liquid level is decreasing a little bit, but it's so small relative to all of the other terms that we can say the velocity head is 0. Air is surrounding the jet, and so that means that the water inside of the jet has no pressure, so we cancel out the pressure head term, and what we're left with is that delta Z is equal to V2 squared divided by 2G. In other words, we're going to let delta Z, we'll call that H, and if we solve for V2, that gives V2 is the square root of 2GH, where H was delta Z. That's the orifice equation. That tells us the velocity of the water that's coming out of that jet. Now remember, the continuity relationship is that accumulation is in minus out. That is, there's going to be a net increase of water inside of the tank if the flow in is bigger than the flow out, and there will be a net decrease if the flow out is larger than the flow in. In this case, there's no flow in, and what we have is that the accumulation will be equal to the flow rate out. So Q out is negative of the accumulation. We're going to see the liquid level decrease because of the flow rate out. As it was presented in the slide prior to this example, the accumulation term is V excuse me, the flow rate out term is V2A2, that's the flow rate out, and the accumulation term is negative the area of the tank dH dt. And it was derived on the previous slide how we get the equation from that the time it takes for the liquid level to fall a certain distance, where the tank area is taken into account. We have the square root of 2G, and the orifice area is taken into account. We want to find out how long it's going to take to fall from H naught to H sub T. So in this example, let's say that we have a diameter of the tank is 500 millimeters. In other words, that's 0.5 meters. From that we can find the area of the tank using pi d squared divided by 4. If you pop that into your calculator, you'll get that the cross-sectional area of the tank is 0.19635 meters squared. And we'll do the same thing with the orifice. The diameter of the orifice is 0.15 meters, and so the area of the orifice we can find with pi d squared divided by 4. It is 0.017671 meters squared. If we now take a look at the amount of time it's going to take to fall 2 times the tank area, 0.19635 meters squared, divided by the square root of 2G, where G is, for SI units, 9.81 meters per second squared, and we put in the area of the orifice, and now we are going to take a look at how long it takes to fall 1.1 meters. And so initially the liquid level is 2.5 meters from the center of the orifice opening to the liquid surface. So it's falling from a height of 2.5 meters, and we need to take that to the 1/2 power. And then the height it's falling to, this is one place where people often make a mistake. You don't put in 1.1 meters because that's how much it's changing. Its new elevation of the water surface above the orifice will be 1.4 meters to the 1/2 power. So in other words, if it's falling, the change in height was 1.1 meters, then after that decrease of 1.1, what's left is 1.4 meters. Alright, if we do the calculations for this entire expression, that works out to 5.017, and this entire expression is 0.3979, and so the amount of time it's going to take to fall is 2.0 seconds. The next part of the example asks how long will it take to fall another 1.1 meters. Now this is a good place to pause and think about the situation conceptually. Remember that the velocity out of the tank depends on the height of the water elevation above the orifice. And so the bigger h is, you can tell from the orifice equation, for a big h you're going to have a big velocity. We started with h being relatively large, 2.5 meters. But then after h dropped, that means that the velocity is going to decrease, and since the velocity is decreased, the flow rate out of the tank is decreased. And so will it take more time or less time for it to fall another 1.1 meters? Well, it should be clear to us that it's going to take more time because the flow rate out is decreasing. Therefore, it's going to take longer for it to fall the same 1.1 meters that it did before. Now in this next example, we have that the initial height is elevation of 1.4 meters above the orifice opening, and h is 0.3 meters. We can put that into the same equation as before. We have 2 times 0.19635, where that was the tank cross-sectional area. We have the square root of 2 times g, and the opening of the orifice, its cross-sectional area. And this time we're going to have 1.4 meters as the beginning elevation and 0.3 meters as the ending elevation. As before, that first term is 5.017, and in this instance the second term is 0.6355. Okay, so that total duration that's elapsed is 3.19 seconds, is how long it takes to fall the second 1.1 meter increment. So just as we expected, it takes more time to fall the second 1.1 meters because the velocity decreased, because the head decreased, and since the velocity decreased, so does the volumetric flow rate.